Assalamualaikum and hi everyone. So today our group would like to talk about application of first order differentiation equation on the topic Newton's law of cooling and warming. We are from RCDCS 1435A and this is my group members. So first one is me, Aina Shaukina, second one Hani Balkis, third Intan Wafa Izzati, and lastly we have Nur Atika. In this video, we will discuss about the introduction of the topic, which is Newton's law of cooling and warming, our problem statement, the problem solution, and the conclusion, and lastly, our reference.
Hi, Wafa. Hi. Why you guys seem so sad?
We are not in the mood.
Why you guys not in the mood?
Maybe you are craving the some food like soup.
This is the proof for you guys.
Wow. Thank you. Thank you very much.
So, this is for you. Enjoy your food.
Thank you. It's very hard. How long I need to wait to eat?
You need to wait for the temperature decreases to 850 Celsius test.
Oh. Okay, so you have to wait.
Yes.
Mm.
I know what to do. We need to follow the Newton's law of cooling and warming to know how much time we need to wait until the soup to reach 88 Celsius. So to find out, let's watch our video together. Yay!
Let's talk about the introduction of Newton's law of cooling and warming. It is a fundamental principle in thermodynamics that describes how the temperature of an object changes over time as it approaches the temperature of its surrounding environment. Proposed by Sir Isaac Newton in the 17th century and provides a mathematical framework for understanding heat transfer. According to this law, the rate of temperature change of an object is directly proportional to the temperature difference between the object and the surrounding environment, assuming the difference is not too large. The law applies to both cooling and warming processes. For example, when an object is warmer than its environment, it will lose heat to the surroundings and cool down. Conversely, if the object is cooler than its surrounding, it will absorb heat and warm up. The rate at which these processes occur is faster when the temperature difference is large and it decreases as the object's temperature approaches the ambient temperature. This makes Newton's law particularly useful in modeling situations where an object is in thermal equilibrium with its surroundings or when estimating how long it will take an object to reach a specific temperature. Widely used in various fields in engineering, it helps to design systems for temperature regulation, such as cooling of engines or electronics. In forensic science, it can be applied to estimate the time of death by comparing the body temperature of a deceased person to the ambient temperature. Additionally, the law is utilized in meteorology, the study of natural phenomena, and in everyday life situations like determining the cooling time of food or the warming time of a cold drink. Last but not least, although the law is quite accurate for small temperature differences, it may not be precise when the temperature difference between the object and the surroundings is large or when other factors such as heat, generation, insulation, or radiation come into play. Nevertheless, Newton's law remains a valuable and foundational concept in understanding thermodynamics and heat transfer.
Okay, next, I will represent the problem statement. So what we solve? This is our situation. In a nice cool day, I would like to make myself a bowl of delicious and warm soup. I still have the soup left over in the fridge. However, it will be too cold for me to drink the soup directly, so I heated it up. Current temperature is now 100 Celsius since the soup is boiling. To drink the soup without burning my mouth, the soup has to be warm. After 5 minutes, the temperature dropped to 95 Celsius. From the situation I explained, we can generate some questions. Assume that constant room temperature is 20 Celsius. First, for our problem, what is the time needed for the temperature of the soup to hit 88 Celsius so that it will be perfect to enjoy? Second, if I took 30 minutes to finish the soup, after 25 minutes, what the temperature will be the soup be? So in this problem, I identify the temperature doesn't decrease in a straight line. Instead, it follows an exponential decay pattern, which means that the soup cools quickly at first but slows down as it gets closer to room temperature. This content is specific to the soup and the environment. It depends on factors like the size of the bowl, the type of container, and how exposed the soup is to air. As the soup cools over time, the difference between the soup's temperature and the room temperature decreases, leading to a slower rate of cooling. In this problem, I investigate this law helps me predict the temperature of the soup at any given time. The equation allows us to determine the time needed for the soup to reach a certain temperature, like 88 Celsius, and also helps us estimate what the temperature will be at any point during the cooling process, like after 25 minutes. So this problem demonstrates how we can apply mathematical principles to model real-world situations, such as the cooling of hot liquids, and use these models to make predictions about when and at what temperature the soup will be ready to enjoy.
For question 1, first let dt be the temperature of soup at any time t. We will start with the equation dt over d small t equal to k times t minus 20. After that, we will need to separate the variable and integrate both sides to get t equal ae power of kt plus 20, where a is e power of c. Now, substitute t0 into the equation. 100 equal to ae power of 0k plus 20, and we will get the value of a, which is 80. Substitute t5 to get the value of k, which is k equal to negative 0.01291. And now we got all the value. We can calculate Tt equal to 88 Celsius. Substitute all the value, and we will get the perfect temperature time is equal to 12.59 minutes. For the next question, what is the temperature at 25 minutes? To do this, we can just substitute the value of T, which is 25, into the equation we have from the question 1. So, T25 equal to 18 exponent power of negative 0.01291 times 25 and plus 20. We will get 77.93 Celsius as the answer.
To sum up, Newton's law of cooling is an essential concept that clarifies how the temperature differential between an object and its environment directly affects the rate of temperature change. Knowing and forecasting how soon an object will attain thermal equilibrium with its surroundings is made easier by the law. The process moves more quickly when the temperature differential is significant and more slowly when the object's temperature approaches that of the surrounding air. This is because of the predict link. The law is useful in a variety of situations. In addition, Newton's law of cooling has implication in everyday life in addition to science and industry. It is useful for estimating the time it takes for a cool drink to warm up to room temperature or for hot food to cool down to a safe serving temperature. It is not only a theoretical framework but also a useful instrument for resolving a real-world issue because of its capacity to measure and forecast heat transfer processes. In the end, the law's simplicity and universality highlight how crucial it is to expanding our knowledge of heat dynamics in a variety of fields and real-world situations.
And lastly, we also list all the references that we use to do this video. Thank you for watching.